Today we're going to talk about the pH scale, and then eventually talk a little bit about the POH scale. And what this is a scale that allows us to measure basically the how acidic or how basic a solution is. And you can see an example of the scale on the right over here. We have a scale that ranges from a pH of 14 right here to down to a pH of 0. And just to understand, if a solution has a pH of 7, that means it is neither acidic nor basic. But as we go down from 7, the solution becomes acidic. And as we move up from 7, the solution becomes basic. And if it's and what that means is that if it's acidic, that means it has more hydrogen ions than it does hydroxide ions. And if a solution is basic, that means it has more hydroxide ions than it does hydrogen ions. Now, so basically, the pH scale is a measurement of the hydrogen ions, and the POH scale is a measurement of the hydroxide ions. And these two actually add up to 14. So what that means is that if you have a solution that has a pH of 5, that means it would have a POH of 9, because these two numbers actually add up to 14. Now, the scale is it's a logarithmic scale. So what that means is every step in this ladder, if you want to think of it as a ladder, is actually going up by a factor of 10, or going down by a factor of 10, or going up actually. It's a negative logarithmic scale. So let me explain what that means. So if you have a solution that has a pH of 1, that means it would actually be 10 to the negative 1. And if something has a pH solution of 2, then it would have a concentration of 10 to the negative 2. Now, 10 to the negative 2 what? What is this unit? So first off, 10 to the negative 1 would be 0.1. 10 to the negative 2 will be 0.01. But what is this unit? This unit is actually in something called moles per liter. Now, a mole is a very, very large number. So a mole is actually roughly 6 times 10 to the 23 particles. So for a solution that has a pH of 1, then you're looking at 0.1 moles per liter, or 6 times 10 to the 22 particles or hydrogen ions per liter. And if it has a pH of 2, so if it has a pH of 2, then we said that it has a concentration of 0.01 moles per liter, which would translate into 6 times 10 to the 21 particles of hydrogen ions per liter. So this means basically that a solution that has a pH of 2 is actually 10 times weaker, than a solution that has a pH of 1, or we can say the pH of 1 has a solution that is 10 times more concentrated than the pH of 2. So going back up here, if you look at, like, example, lemon juice has a pH of 2, and if we average tomato juice to have a pH of around 3, then lemon juice is 10 times more acidic than tomato juice. Now, the advantage of a logarithmic scale, I mean, we can see here in chemistry, but you're going to probably come across a lot of logarithmic scales in your high school. And here's an example of one in biology. And here's a logarithmic scale showing you the mass of organisms on your x-axis. And again, the advantage of a logarithmic scale is it allows us to put things that we normally cannot fit on an axis when you consider the wide range in our masses. Like, for example, a whale has a mass of about, I guess according to this scale, somewhere in the neighborhood of 100,000 kilograms, which is 10 to the power of 5, whereas our x-axis, all the way to the left, you're looking at organisms that have a mass of 0.01 kilograms. That would be 10 to the negative 2. Now, if you consider this, you have a range here of about 10 to the 7. So that's like 10 million. So you're looking at the smallest organism is 10 million times smaller than the biggest organism. And it would be very difficult for someone to put that on an x-axis unless the scale was logarithmic. So let's going back to pH. So we can actually calculate how many hydrogen ions there are in a solution. So for example, if I have a solution that has a pH of 5, then the formula would be, we have 10 to the negative 5 moles per liter of hydrogen ions. So that would be equal to 0.00001 moles per liter of hydrogen ions. Okay, and if we have a solution that is a pH of 3, then that would be 10 to the negative 3, which would be 0.001 moles per liter of hydrogen ions. And then we can compare. We can say, well, how much more concentrated is a pH 3 solution relative to a pH 5? Well, we can say how much more hydrogen ions does it contain, and we can just do the math. If we have a pH 3 solution is 10 to the negative 3, and a pH 5 solution is 10 to the negative 5, then this divided by this gives you 10 to the 2. Okay, so that means that our pH 3 solution is 100 times stronger or more concentrated than our pH 5. Okay, so here's another example of using the pH scale. So which is a more concentrated acidic solution? This one. This one has more hydrogen ions than this one. So this is the stronger solution. Okay, now how many times stronger is it? Okay, so same idea. So a pH of 1.5 would be 10 to the power of negative 1.5. A pH of 6.5 would be 10 to the power of negative 6.5. So when we divide the stronger solution by the weaker solution, we get a difference of 10 to the power of 5. And that would work out to 100,000 times more concentrated. There are 100,000 times more hydrogen ions in a pH 1.5 solution than there is in a pH of 6.5. Okay, and lastly, why is it important to understand this pH scale? Well, it's important for many reasons, but I'll give you just a few examples. One is for understanding how your stomach works. So your stomach uses a very low pH of around 2 or 1, and it does this by pumping out hydrochloric acid, and it uses this very strong acidic solution to break down protein. To understand, it's very important to understand pH for your blood. Your blood has a pH of around 7.34 to about 7.45, and things that would drive the pH past 7.45 or below 7.34 could be life-threatening. So it's very important to understand pH when it comes to your blood, and it's important for understanding it in terms of marine biology. The ocean has a pH of around 7.5 to in the low 8s, around 8.4. And with excess carbon dioxide emissions, carbon dioxide in water actually give you carbonic acid. And so guess what that would do to a solution that has a pH that is above 7? Well, when you add carbonic acid, it's going to drop the pH to below 7.5. And that's not good for organisms that build shells, because the acidic solution will actually attack those shells and make those organisms vulnerable. Okay, so that's it on pH. Talk to you later.